Ladies and gentlemen, welcome Andrew Geiszler. He will be speaking on living, working, and growing in glass houses on Mars, I presume. Welcome, Andrew.
I have the next slide feature. That's nice. All right. Good to see we have a full house. I was hoping I'd have more than 4 people. So anyway, so I'd like to talk about some research I've been doing on architecture for a Mars settlement, because as I'll get to, it really requires different thinking due to the different constraints than on Earth. So this is just a picture of a geodesic dome that I drew up in CAD to kind of be a little teaser. So anyway, so this is what Mars looks like right now. I'm sure that's a giant surprise to all of you in this room. But what we're hoping for is in 50, 100 years that it'll look more like this. But how do we get there? And so of course the first steps is something like that. But what's the next step after that? So the first question is to build above ground or below. Building above ground is much easier. If you think about it, most architecture on Earth is above ground, because otherwise you have to dig a big hole first. Mars is a rocky planet for the most part. Probably not that many natural caverns. We haven't found any yet. There may be a few, since caverns are formed by water action. But ultimately, to do any significant excavation on Mars will require explosives. I considered making a presentation called Blowing Up Mars for Fun and Profit, but I decided to do that one next year. Ultimately, though, one of the biggest motivations for building on the surface is agriculture. As the previous presenters have mentioned, brothers gotta eat. So Mars 1 proposes to do indoor, artificially lit aeroponic, hydroponic agriculture, as did our previous speaker. But I'm not convinced that this will work. For one thing, particularly if you're using solar panels as a power source, you're getting 44% sunlight, and then you're getting 10% of that, and then you're going through power conditioning, and that's going to be another 50% cut off, and then you're going into LEDs or some kind of light source, and that's another 70%, and you're getting down to 2% of the natural sunlight. Why don't just use the natural sunlight? That's much easier. And so ultimately we're going to need transparent surface structures. So first of all, in any engineering problem, you need to identify your constraints. So in this case, we have environmental constraints. We have atmospheric pressure. Mars ranges from 30 pascals, 30 newtons per square meter on the summit of Olympus Mons to 1.16 kilopascals, so 1160, in the basin of the Hellas Planitia. But the sea level, if you can call it that, the Mars average is 600 pascals. Earth's sea level average is 101.35 kilopascals, so that's 160 times Mars. So Mars is about 0.6%. So that's a huge pressure difference. And to put this all in context, the Armstrong limit, that's the pressure at which water boils at human body temperature, is 6.3 kilopascals. So that's that is the basement, that is the bottom, lowest pressure at which we can survive in any capacity. You actually can't breathe at 6.3 kilopascals. You need a little higher pressure than that, but we'll hand wave away that one for a moment. Temperature. Temperature on Mars cycles between, in the tropics, it's nice and balmy, 100 degrees below zero, up to, on a really hot day, maybe almost 30. 30 is actually 85 degrees, so not bad. 85 degrees Fahrenheit, sorry. I'm getting too engineering up here. Gravity. So we've got 38% gravity, 3.71 meters per second squared versus 9.8. Radiation, of course, radiation. Everyone's talking about radiation, but the important one to consider here is the ultraviolet. Interestingly enough, the total integral of ultraviolet radiation received on the surface of Mars is the same as that which is received on the surface of the Earth. The difference is the frequency distribution. Mars gets more high energy UV than Earth does. And so there's UVA, which is not so hard. That's the stuff that causes you to tan. There's UVB, which is the stuff that causes you to burn. And there's UVC, which boils bacteria alive. Mars gets more UVC and UVB. On the surface of the Earth, we get almost nothing but UVA. Also, a smaller consideration is wind. Windstorms on Mars can be, well, slightly brisk. However, because of the thinness of the atmosphere and the low temperature, when you calculate out the aerodynamic pressures, this really is about the equivalent of a 25-mile-an-hour breeze on the surface at sea level on Earth. So it's actually not that bad. So that's one of those few issues I took with Andy Weir's book, is the wind is actually not that fast. And so let's consider what these things come down to. So atmospheric pressure, that's going to be, since you're going to be pressurizing your structures, that is going to be, you're trying to explode your structure outwards, essentially. And so that's going to be putting tension on, circumferential tension on the elements of your structure. Temperature, of course, is a thermal consideration, and that deals with an expansion, contraction in the materials, and also how the materials hold up on a chemical or molecular level to thermal cycling. Gravity is generally a compressive element. As I'll mention in a moment, gravity is the main consideration on Earth, and thus that's why structures on Earth are built with compression in mind. The UV component is mostly difficult due to the need in this particular case to maintain transparency. So obviously, if you don't have to maintain transparency, you can just have a giant slab of concrete and that'll block out all of your radiation. But currently we don't have clear concrete. Wouldn't that be cool? And then of course, some materials, particularly plastics, as anybody knows who's left anything plastic outside for any period of time, they tend to degrade in sunlight. And oftentimes they turn brown or they become opaque in some respect. And so we need to have a material that's going to last in a harsh, relatively harsh solar photic environment for a while. You don't want your things to just immediately degrade. And then, once again, wind is going to cause some shear forces on your structure. Shear is the acts of bending or trying to cut something. So, as I alluded to earlier, what is the difference between building on Mars versus Earth? Well, on Earth, the major component of all architectural design is gravity, is compression. You have the weight of whatever is above pushing down upon that which is below. And so all structures on Earth, you can see by their design, there's lots of vertical elements and then with horizontal beams across. And that's all due to gravity causing compression in the structure. Square structures with perpendicular elements. Sorry, I'm getting a little ahead of myself. And so you can see that in a standard Earth structure, is you have vertical pieces stacked on top of them, horizontal pieces stacked. It's all arrayed vertically or horizontally to cope with compression. So Mars' gravity, of course, is less than Earth's, and the atmospheric pressure is much lower. And so you're going to have this giant outward pressure causing tension in your structures. And of course, it depends on how much pressure, but even at relatively low conservative pressures that humans can survive at, you're going to have a lot of tension, as I'll show in just a moment. And so this primacy of tension over compression really needs to have a rethink of how we design our structures. So I'm going to give you a little sort of flat plate example. So imagine you have sort of a giant, you could even call it an infinite flat plate that has a pressurized environment underneath it and Mars pressure above it. So let's say our flat plate is made out of soda lime glass. That's what normal window glass, what glass in most car windows is principally made of. That's the standard glass that's been around for thousands of years. Has a density of 2,500 kilograms per meter cubed. So a cubic meter of this is going to weigh about 9,300 newtons on Mars, where it would weigh just shy of 25,000 newtons on Earth. Big difference. And so if we consider, since we're looking for a thickness here, we're gonna abstract this out as 2,500 kilograms per meter squared times whatever the thickness is, will give us, or 9,300 newtons per meter squared times this thickness is going to give us our mass estimate. So let's consider a gas differential of 25 kPa. So 25 kPa, that's a pressure that you can both not have your blood boil and you can potentially breathe at, particularly if you have supplemental oxygen. 25 kPa is about the pressure you'd experience if you're on a commercial airliner at cruising altitude and you decide to take a walk outside, just to give you an idea. So it's about 75% of the pressure on the top of Mount Everest. So that's going to cause a pressure of 25,000 newtons per meter squared. So here's my picture of pressure underneath, mass on top, pressure pushing up versus the compression of gravity pulling down. And a little quick arithmetic, and we get our flat plate would have to be 2.7 meters thick to overcome the pressure just through weight. That's pretty thick. That's a serious chunk of glass. If we look at, say, polyethylene, so that's what a lot of plastics are made out of. That's what plastic milk jugs are made out of. Probably one of the most common plastics in use on the planet. So that's only 900 kilograms per meter cubed. And for that, you'd need a slab 7.5 meters thick to overcome the pressure pushing out just via compression of gravity. Okay, so we're now on Mars. Where do we get our materials? As has been alluded to many times, launch costs from Earth are usually expensive. And raw materials tend to be heavy. They tend to be massive, or at least you just need a lot of them. And so the total mass necessary is going to be high. And so really importing structural materials from another planet doesn't really make sense. Really, the only things you should be importing from Earth would be finished products, computer components, chips, not potato chips, computer chips. But really complicated things that require a high-tech industrial base that you're not going to have in a 6-person habitat on Mars. So the rule of thumb for Mars is going to have to be use local or go without. Figure out how to do it with what you can find around, or deal with the lack. Luckily, there's a lot of potential in both the Martian atmosphere and in the soil. So here's a graph probably most of you have seen before. We all know that Mars' atmosphere is mostly carbon dioxide, but it is important to notice traces of nitrogen. That will be very useful because a lot of organic compounds have nitrogen as minority constituents. The soil, however, is even more interesting. So this is a compilation of data from soil samples taken by Spirit, Opportunity, and Curiosity. We find alumina, which is aluminum oxide, silica, silicon dioxide, calcite, calcium oxide, soda, sodium oxide, and strangely enough for the red planet, or the rust planet, not all that much iron oxide, which is interesting. There's actually more nickel out there than iron. Nickel is also a metal that can be used for structural materials. Okay, rocks. Everybody loves rocks. Curiosity has found feldspars, which are alumina silicates with potassium, sodium, calcium added. Pyroxene, which is a very complicated and wide range of mineral types, but with all the sort of same crystal structure. But there's lots of different metals that could be potentially drawn from those rocks. Olivine, which is another silicate of magnesium or iron. Opportunities also found gypsum. Gypsum is very interesting. That's calcium sulfate. Sulfate is useful for many things, particularly in agriculture. But ultimately, for the early days, we need to try to stay away from rocks. Hard rock mining is very difficult, requires huge investments of equipment, heavy equipment usually, lots of energy to really make that go. So if you need to use it, it's there, but it's going to be tough. Okay, what can we make as far as plastics go? Ultimately, the atmosphere of Mars is plastics feedstock. We have our good friend, Dr. Zubrin's Savadier reactor fuel system, and from that, we can make methane. From methane, it's pretty easy to start making things like ethylene. From ethylene, you can start making polyethylene, or polypropylene, or polycarbonate. Polycarbonate is what a lot of lab plastic pieces are made of. Also, a lot of eyeglasses are made of polycarbonate because it's very shatter resistant. Polyethylene terephthalate is the most common plastic used to make plastic water bottles, the ones that you get at wherever, the thin ones. Polymethyl methacrylate is also known as acrylic. That's plexiglass. And then polysiloxanes is the general term for the group that includes silicone. Polysiloxanes are different because their backbone is actually made from silicon, not from carbon. And there's a lot of silicon on Mars. The difficulty with plastics is in this UV environment, they're all going to require chemicals called UV stabilizers. UV stabilizers are generally aromatic compounds that absorb ultraviolet radiation and re-release it as heat. And generally, UV stabilizers are all benzene derivatives. Now, benzene is why you should not drink gasoline. The aliphatic hydrocarbons in gasoline, the octanes, the nonanes, etc., those are not actually that toxic. It's the benzene that, if you drink it, it goes straight into your DNA and causes your cells to just fall apart. Luckily, there are new ways coming up, particularly since the sort of the shale natural gas boom the last couple of years, of creating aromatic hydrocarbons from straight natural gas, and natural gas is mostly methane. So there we are. So ultimately, plastics are going to be your best bet as far as ease of manufacture, low energy necessary, but they're still going to, but despite even adding UV stabilizers, they're still going to have a short lifetime in the Martian environment, whether due to UV degradation or thermal cycling. Well, so that's a good question. Obviously, we haven't sent much plastic to Mars yet to know for sure. It's pretty easy to find, say, plastic sheeting for greenhouses on Earth that is marked as guaranteed for 4 years. And given that the UV total energy is about the same, maybe conservative and call that half. I don't know. 2 years. I mean, it'll be hard to tell. They'll need more research on that to be sure, but it seems likely that you'll at least get a couple of growing seasons out of a plastic kind of structure. Yeah, as I mentioned, thermal cycling. Okay, so what can we make in terms of glass? Glass is a nice transparent molecule. So as I mentioned before, soda lime glass is the most common type of glass. It's been around for thousands of years. It's strong, but it's brittle. Most of you probably have noticed that glass tends to shatter if you hit it. Another type of glass, Alumina Silicate glass, so Gorilla Glass you've probably all heard of. This is the type of glass that has become very popular to put on smartphones and tablets because it can be made very strong even in very thin setting. So the difficulties with aluminosilicates is they're harder to melt, harder to form. It's a more difficult, more high-tech process. They tend to require much more careful quality control, particularly in terms of the metals and the ions and the various chemical processes that go into making them. But they do have excellent physical properties. Oh, I didn't do that. Another possibility is borosilicate glasses. Probably most everybody has heard of Pyrex. It's popular in laboratory settings as well as in tableware. Pyrex also has excellent physical and thermal properties. Pyrex bowls are well known for being, you can drop them from head height and they just bounce on concrete. It's really impressive stuff. The difficulty is, as the name implies, borosilicate involves boron, and to my knowledge, nobody's found any sort of substantial deposits of boron anywhere on Mars. It's probably there, we just haven't found it yet, but it may be, but we shouldn't bank on things that we're gonna have to go prospecting for. We should stick at this point with stuff we know is there. There's lots of other types of glass. Fluorosilicates that have fluorine, lead glass. Fused quartz is basically pure silica, but none of these really have it when it comes to kind of the mix of physical and thermal properties we're looking for. Fused quartz does, but it's even harder to make than alumina silicates. So let's stay away from that one. The nice thing about glass is that glass of any substantial thickness is going to be essentially impervious to UV. Glasses can be tempered in such a way that they're essentially immune to thermal cycling. You get sort of this semi-crystalline phase going on where the amorphous stuff expands and the crystalline part contracts, and as a result, the whole piece can go through enormous temperature changes and it doesn't change its shape and it doesn't expand or contract. So that's really impressive. Okay, so we've got some of these parts now. Now, how do we put it all together? So it's important to note that glasses and plastics have different mechanical properties. So glass is very strong in compression, but it's very weak in tension, and don't shear it, it's going to shatter. Plastic is relatively strong in tension, but is much weaker in compression, and it also tends to be fairly strong in shear. Plastics bend and they don't shatter. So we can consider the different portions of our structure and use different materials to control for that. We've also got some metals available, aluminum, iron, nickel, but and those are strong compared to the other two, they're strong in tension, compression, and shear. But they're relatively scarce. They're going to be difficult to mine, difficult to process, so we need to consider that we should really restrict our use of metal to small niche uses like tensioning cables. Okay, so I'd like to quickly introduce the concept of tensegrity. So tensegrity is a structural principle that's been around for about 90, almost 100 years, and is the use of isolated components in compression inside a net of continuous tension in such a way that the compressed members do not touch each other and the pre-stressed tension members delineate the system spatially. So this is how you build large stadium domes, for example. Ultimately, just geometrically, the strongest shape really in tension or compression, or at least in a combination of the two, is the triangle. And the best volume to surface area ratio shape is the sphere. So and this is sort of a basic thought experiment element of tensegrity. You have the brown bars are the compressive elements, and the silver lines are the tensioning elements. And so this is how tall communications towers work. You have this tall compressive element held together by a net of tensioning guy wires. Okay, so what happens when we put triangles and spheres together? We get a geodesic dome. Part of this is just practical. Humans don't really build large, perfect spheres. We can cast little ones, but it's not practical to try to build a giant, perfect sphere. And the best analog we've got is a geodesic polyhedron. So we can have a half sphere for tall crops, for building structures within, or you can build more flattened geodesic structures if you just have short crops. Another option is to analog this out into a cylinder. And so a cylinder combines the structural rigidity of the geodesic dome in 2 dimensions with ease of construction and modularity in 1 dimension. Another idea I just had recently is to have a sphere toroid. So to have sort of a half of a donut shape on the inside and then an ellipsoidal dome over the top. And as you can see, there's a gap in between. And that gap and that gap's sort of greatest thickness is when, for example, the sun is straight overhead, and so you get the largest mean free path through the structure during that time of day, which of course is going to be your highest radiation pressure. And so you can fill that gap in with air or even water for radiation shielding and thermal considerations. Okay, so you tell them what you're going to tell them, you tell them, and then you tell them what you told them. So ultimately, we're going to need to use native materials. It's very feasible. They're there for the taking. We just need to keep in mind what's best for different things. The greatest challenges early on will to have sufficient energy, both electrical and thermal, for mining and processing. Glass is not just going to pop out of the earth. And it's important to note the different physical and environmental constraints requiring a different mindset, a different paradigm, a different philosophy vis-a-vis how things are built on Earth. And image credits and questions. You, sir.
You might be happy to know that in 2013, students from the University of Hawaii reported a boron in Martian clays that
Oh, very nice.
So the second thing is that one of the minerals, the organic minerals that might be there on Mars is the benzene hexacarboxylic acid.
Mhm.
Published a paper on it about
Okay.
20 years ago. So you do have benzene, but it's actually quite fragrant. And the art people use to wash it in, so it's not quite as bad.
I won't take your word for that. I'll take your word for the boron. Dr. Terry.
As I recall, the total radiated spectrum insulation on Mars is about equal to the insulation on Earth, which is Mars spectrum, which is hard.
Right, that's what I said.
And the question is, if you're trying to do total radiation for agriculture, you want to consider what's called photosynthetic active radiation.
Yes.
And so how do you figure to control that using a lot of glass? Because the glass is going to be opaque to all the light.
Okay, yeah, so I think the point he's bringing up is that plants do need some UV, and so you're going to have to control the thickness of your glass or its composition to allow some UV. And yeah, and different glasses have different extinction coefficients in UVC, UVV, UVA. So I think that's very possible to engineer around. Okay, how about you back there? Sorry, I'm not ignoring you. So plants are pretty hardy, and especially for short-term, annual type of crops. I mean, if your tomato plant gets a cancer, sure, it's not great, but you can still eat it. It's not that big of a deal. Yeah, I mean, it's possible. See, I'm a bioengineer by background. I've actually worked with a fair amount of radio tracers in research I've done. I don't entirely buy the line on GCR causing cancer. Let me clarify that. So basically, as I understand it, if you can, if you have sort of a big graph, 0, 0 down here, the data points for radiation sickness and for causing cancer are all up in this upper right-hand corner. And basically what they did to model that is they just took a straight line down to 0, 0. That's not generally how things work in biology. Usually there's inflection points, there's exponential distributions. And so you should have something, keep on doing that, sorry about that. You should have a curve that does something like this as opposed to just being a straight line. And when you consider that, the GCR dose that is officially supposed to cause whatever it is, 1% cancer, 3% cancer, is probably more like 0.3% or 0.03%. So, okay. All right, sorry.